Okay, so I see that Romina, you are here. I'll just go over. Let me see. I guess, Romina, I just want you to confirm to me that you are seeing my screen. Do you see my screen right now? Do you see my screen? Let me check. Okay, that's good. Let me start then. So our project, or your project, that is traveling salesman problem, and we denote this one as TSP, and the problem is defined as having a person traveling n cities, where the n cities or points, and it starts over n cities. It goes only once at each city and then comes back to the initial city. This is a tricky part. So this has to be included. If this was not here, it could be easier. So we have to find what is the shortest path. In the homework or in the project, what I'm requiring from you is to do the following. I'm requiring to, let me see here, give me a second, home. Where is this insert? I want to insert the text box. I want you to check what is the relationship between the shortest path and summation of diagonals, okay? Diagonals. And then shortest path and the areas of the triangles created. If not areas, I'm going to explain what this is. The first part is relatively easy. The second part is going to be a little tricky, but let's see what I'm trying to say. So let's assume that we have these points randomly distributed, and there are 5 of those. And we know that the distance, let me write this one here. We can say that A12 plus A23, this is larger than A13. Now, what I'm trying to say here is that the summation of this path and of this path is larger than this diagonal, which joins the endpoints of these two sides, okay? That's what I want to say. So A13 is this diagonal, and I'm calling it diagonal the line which connects two subsequent paths, okay? And probably the best is it could be to have these paths like this. So assume that this is an arrow, okay, going in this direction. Now, I don't know if I can change the type of line here. Probably I can. Okay, good. I can, no, the other way around. Anyway, I was not very lucky. Let's see. But we should not waste all the time with this. Okay, so we assume that we are following these paths. Arrow again here. Okay, good. So we're moving in this direction, assuming that this is the true path. We could make this a little better. I did. Okay. Here we go again, and here we go again. Fine. Now let's assume that the shortest path that is going to be picked up is A12 plus A23, and so on. Then we can construct this other. Let's assume that the next two subsequent path is going to be A23 plus A34. This is going to be larger than A24. I hope you understand this part, but what this is this diagonal which is joining these two, okay? Similarly, the next path which is left is A34 plus A45. This is larger than what is left here, 35, I guess, 35, yes. And it's going to be a diagonal which is going to join, I guess, is a side turn for this plus this, okay? So try to follow how, and then the next path, let's say we went from A34 to A45. Now we have the path of A45, what is this? Yeah, we have A45 plus A51. This is larger than the diagonal which is joining these two. So A45 is this one. And let me make this a little more extreme and like this. Okay, so we have this line, the weight, let's put it a little bigger. And also, so these two lines that we are considering are these two, okay? And we don't need to do all of this work in detail, but let's assume that we have this A45 plus A51. This is larger than A41. Okay, so here we have another diagonal, which is going to look like this. Let me pick up this one here. Okay, so this might look a little confusing here, but if you write the algorithm here, things can look a little better. Now, there is a relationship between the whole path that we follow. Okay, so imagine for a moment the whole path that we follow is a summation of these terms which are shown here. Let me do them like this. No, sorry, I wanted to add these. So imagine for a moment that let's have this inclined. These plus these is somehow related to the total path that we follow, okay? And meanwhile, I just want to get a partial confirmation that it's fine to make it with 5 points only. Well, when you talk about 5 points, we can also do it with 7, okay? I just said, so it's not a, I'll discuss also a little bit short code, Romina, okay? With 5 or 7, it should not matter much. So, but let me go on what I'm trying to say here. So this is what we're trying to do. Okay, that's the first idea is to construct a relationship between the path, the shortest path, and the summation of all the diagonals. That was the first part. Good. The second part is the following. Assume we want to check the relationship between the shortest path in a polygon or in a shape and the area of the polygon, okay, and the area. Let me call this one, let it make it like this, and I'll try to make this clear very easy. So imagine that this is your polygon, okay, and then you draw a line which is like this, and this line it's passing at the lowest point between these, okay, between the polygon. So it's easy to figure this out, and then we can easily determine the area here, the area of this polygon, by doing the following. Imagine for a moment if we had some lines that extend like this from here down to here. Okay, probably I can better explain this one on a piece of paper and I can share this with you. Imagine now here we have a polygon, okay, and here we have another polygon. So when I'm talking about polygon, I'm talking about the area which is covered between these edges. 1, 2, down here and here. This is like a trapezoid, okay? So I'll explain this one when I go to the code, okay? So we need the area of the polygon. Good. This was the second part. So this was diagonals, and this was the so-called polygon. Now let's go to the code. Now, to make things a little more easy, imagine for a moment, I've written here, I have a code here that I can share with you, but imagine for a moment that I'm running it and I will show to you what I get as a result. And then, okay, so here I randomly generate some points which are shown here, okay, and then here I'm drawing the graph of the dependency between the sum of the diagonals and the shortest path. Okay, that's what I was trying to, what I was asking, what I mentioned before a while. Okay, again, here we generate another set of random points, and we want to see how. So I think, let me try to remember what was this last figure. The last figure, it's plotting the relationship between, let me see, x-axis is the diagonals. Okay, so it looks like, and the y-axis is the distance. So the y-axis is the shortest path, okay? And this other x-axis is the diagonals, as I said. So let me run this again. Okay. So here we go. And now let's see how we can construct this one. For a moment, let's see what we do. So if we look at the code, how we run it, imagine for a moment that we have 4 points, right? And then here the code runs, and it starts at point 1. When this starts at point 1, we assume that we are going to test all the possible combinations. Okay, so here I did this one for 4 points, not 5 like in the slide. And out of these 4 points, we search. If you see here, we say that for I, we assign that first point is 1. Then we're checking for I from 2 to 4. So imagine we can go then from 1 to 2, and then we can go from 1 to 2 to 3, and then we can construct 1 to 3, 1 to 2 to 3 to 4, right? And then with this combination between the 4 points, the distance is equal to 2.69. And this distance is found here. So once we construct, so this is the distance, okay, that we want to determine. We can have a look at the code in detail, of course. But meanwhile, let's see, this loop, let's say it found one combination where it goes from point 1 to point 2 to point 3 to point 4, and then it goes back from 4 to 1. Then we remove, we cut a little short this vector x because we want to search the other combinations. We make this one 1, 2, and then we start again. We say we go from 1 to 2, but now we don't go to 3 to 4, but we go 1 to 4. And this, imagine, remember the previous combination, it was 1, 2, 3, 4, which is this line here, okay? And now we have 1, 2, 4, 3, good. And now with this new combination, the shortest the distance between this combination of the 4 cities, in the first case it was 2.69, now it's 2.11, so it looks like it's shorter. Most probably we're going to pick up this one. Then, but now we did 1, 2, 3, 4, now we did 1, 2, 4, 3, and now let's cut short a little bit this vector x. We have go like this, and then we get 1, 3, 2. Okay, we go from 1 to 3, then we get 1, 2, 3 to 2, and then when we go to 1, 2, 3 to 2 to 4. Okay, this is, if you get a pen and paper, you're going to see that these are all the possible combinations. Okay, and then this new distance, apparently, if we do these combinations, remember the first distance between the combinations of the 4 cities, the distance was 2.6961. Then it's 2.11, and now it's 2.05, so it's getting shorter. That's what we're looking for. We're looking for a shorter path. That's good. And now we cut this a little shorter. We go back. We construct another path, which is 1, 3, 4, 2. Okay, this is another path. We construct. We find this distance again is 2.11, and then so imagine you have all of these paths which are shown here, and then we go back again. We construct 1, 4, 2, 3. With this 1, 4, 2, 3, we find another distance. And notice something. We're finding all these distances for different combinations. But there is something strange that for 4 cities, the total combinations, the distances, you see this distance twice. 2.1103, 2.1103. Again, 2.05, 2.05. So we have some doublets, and we can check what this really is. So we go like this, and we have the final combination, which is 1, 4, 3, 2, and the distance is 2.6961. And interestingly, we had this distance initially. Okay, so that's something strange. Why do we get this? Now, these were the distance, the 6, all the possible combinations that we can travel around, and we did this with brute force. We tested all the different possibilities, and then these were the distances. And in a variable xx, we have written, no, let me think for a moment. This was TSP2. What, okay, apparently. Okay. No, I thought I had this for a moment. Give me, no, x is 1. Okay. Then allow me, so here we can write down all the possible combinations. This is xx. Let me, I thought I had redone this one. Allow me to run this again. The results, okay, this is what we see here. So the randomly generated points are shown here, and this is the result. And you can see here that this is the shortest. I forget what the x-axis was here. Allow me to check this again. So D was the shortest path, or the path between, not the path between all the combinations. So this is, no, sorry, this is the diagonals, and this is the the path that we are interested in. So we have to look in the y-axis. And since we're looking for the shortest path, it looks like for these points that we have here, which are given here, we can move around. So this is the shortest path, which is shown here, which is less than 1.5. And let's see what are the distances. D is the distances of all the paths, and diagonals is the sum of all the diagonals. We are searching for the smallest, shortest path, which apparently is this 1.49. And we see that for the shortest path in traveling salesman problem, this corresponds to the largest sum of the diagonals. So we notice something which, to my knowledge, I've never seen this before. So this could be an indication that the traveling salesman problem, if we're trying to find the shortest path, maybe it is best to go and search for the largest summation between the diagonals, and probably that correspondence will be linked with the shortest path. So we find an indirect method. This could be an option. That's what we are trying to test, but it's a good sign. Okay, so the TSP problem, it's an unsolved problem. So far, no one can provide a direct answer, and we are trying to find an intuitive approach. Okay, and this x-axis here, we have shown here this x-axis. It has all the indications now, which shows that the path 1, 2, 3, 4, it has the distance is 1.49. Okay, the path 1, 2, 4, 3, the distance is 1.6. This is less. This is important for us. The path 1, 3, 2, 4, the distance is 1.65. And meanwhile, this 1.65, which is the longest path, this has the shortest sum of the diagonals. Okay, so we see an inverse relationship between the sum of the diagonals in the between any two subsequent paths and the path itself. Okay, and then we go again 1, 3, 4, 2, 1, 3, 4, 2. The distance is 1.60, and remember that this 1.60, we have seen this also here, which looks like the fourth row here. It is equivalent with the second row here. What is the reason? The reason for this, let me try to see, is that this path is the counter. So this is the counter of this path. So if this is rotating clockwise, this is rotating counterclockwise. So you can see that this is going 1 to 2 to 4 to 3, and this is going 2 to 1 to 3 to 4. Okay, so, or let me read it like this: 1, 2, 4, 3. So imagine you're going 1, 2, 4, 3, and the fourth one, let's go counterclockwise. This goes 1, 2, 4, 3 again. Okay, that's why these are symmetric. Okay, so what I want to say is that all of the possible combinations of pairs, there will be 6 in this case, but they are in pairs. Okay, and this one we can also distinguish using a small code. So let me tell you. Let's see, for example, what do we have here? We have, let's try to determine fast Fourier transform of absolute, sorry, no, let's do it like this. We do norm of the absolute value of the fast Fourier transform, FFT, of XX of the second row. Okay, this is the second row, minus, let me see where this ends. This is here. This is here, minus, I guess this will be correct, minus absolute value of the fast Fourier transform of this vector XX, but the fourth row. Okay, we have the fourth row here, and if we check this one, the norm is equal to 0. So we can see that this is the same path, it's just only, it's a permutation of the same order of numbers. So, okay, and then let's see where we have another symmetry. We have 1, 3, 9, 2, 2, 1, 3, 9, 2, 2. So the first row here and the sixth row, they are the same path. Let's check if this is true. The first and the sixth. This is the sixth, and the first row, it's here, we get another 0. Any other linear combination between the first and the fifth, it's non-zero. So this is, you can check, if you want to write the code, if the number of cities is much larger, one can automatically check whether you have the same path or not by just running this simple code here, which is comparing the Fourier transform of one row with the Fourier transform of another row. That's good. So this is, and as I said before, this is very promising that we observe that as I said before, the y-axis is, we are trying to find the minimum path, and we observe that this is inversely related to the summation of the sum of the diagonal term. Good. Now, so that was one thing, and if we go back to the code, I can, these two codes, which I can provide you, are a little different, and the point is that if we check this TSP, Traveling Salesman Problem 02, here we generate 4 points, we generate random points like here. So points, what they are, let's see what they are shown here. These are the points, and we generate 4 of them, but here we say that if we have 4 rows of 4 points, we add the 5th row, where the 5th row has the first row, and we do this because we want to plot the closed path like we do this. So in order to plot this, we fictively add this row, okay? Good. So after we add these, we want to determine, so if you have these 4 points, we want to determine all the possible combinations of the distance of the distances between any two cities. So for a moment, let's run only this section. So the variables are gone. We have nothing here. Okay, let me take this out. So if we come here, we run, let's say that we run only this part, and we evaluate this section. So the points, here we have the 4 points, okay? Then we add another line, and the points now, it's not this, but it's a little, it has one more row, where the first row, it's at the beginning, and then we plot this figure, and things looks good. Okay, so we plot this figure, here we have it. This was randomly generated, okay? Then we want to find the distance between any two pairs of points, like the distance between any two cities. We denote here DDD is a matrix which is full of 0, okay? It looks like this, good. Then we generate here, we run this for loop, and we find the distance between any pair of any two cities. So that's what we get. From a DDD full of zeros, we get here this one, which denotes the distance from city 1 to city 2. Because in this matrix, this is DDD, first row, second column. This distance is the distance between the first city and the third city. This is the distance between the first city and the fourth one, and so on. Then what we do is that we can update this DDD by adding it the transpose. So if we do it like this, the DDD, it will be, we just add to this matrix, we add its transpose, and that's what we get. What this matrix now is showing that going from city 1 to city 2 is the same like going from city 2 to city 1, okay? That's what we're trying to say. Or this 0.38, this shows the distance from the second city to the third city, which is going to be equal from the distance from the third city to the second city, okay? That's how we read this. Good. So we started all of this by randomly generated some points which are shown here. We found the distances between any pair of two cities, so from here to here, from here to here, and from here to here. And probably this figure can be a little better if we do it like this with O. So let me plot this again, evaluate selection. Okay, so we made some circles here to denote them better. Now that we found this DDD, we run the other part of the code. When I say the code, where we go using brute force to find the distance between any the total path between traveling all the possible combinations, and this is what we get. Okay, now this was the part where we want to determine the relationship between the shortest path of a TSP and the sum of the diagonals. Now, so you can run these two codes, actually how they are. And the other part, the second part, is to determine how is the relationship of the shortest path, which, by the way, what is the shortest path we're looking for? Is this range, is this list of distances where we hope, we aim for this, right? And this is only for a city, for a list of 4 cities with 5 or 7 or 9 or 11. Of course, it's going to be a little more complex. So now let's see how we can determine the areas. Now, the areas that we do here, we can find this as, for example, I can give short hints here, and you can develop this on your own. So for a moment, let's imagine, let's try to find what is points. These are the points, and we wanted to determine what is the minimum of the y coordinate, so minimum of all the rows, second column, this is 0.04, sorry, 0.034. So this is the minimum value in y. Now, since this is the case, we can try to determine a point. Okay, wait a second. I think there is also something important which I can add. Okay, I think I don't have it here. So points dash 1, this is equal to points or better, points is equal to points. We can do it like this, and points, all the rows, second column can be 1. This is equal to points minus, so sorry, 0.011, 1, all the rows, second column, minus 0.0344. Now, these points 1 is equal to the points, just that they are shifted. All of them, they are shifted by an equal amount, which is this. And by doing this, we have done this. So we have changed the reference frame, and we are trying to, so we want to calculate the areas between any 2 subsequent points. At this part, I think that we need to determine what is the area of this trapezoid between points 1, 2, and so on. How can we do that? Let me think for a moment. Let me get this added to this part of the code. I can say here a minimum, which is equal to this, and then we can say that here we can make use of this in here, this minus a minimum, which is not a min. We are in the, okay, so we have this point n. So now this point is all updated. Now at this moment, what we need to determine is that I think that we need to identify. So let's say that we go from which point? Let's start from any point actually. I think we have to do that any x2. So let's do it like this. For I equal from 1 to, what should we do here? Let me think for a moment. I'm just going to give a little hints, and I hope you can follow this one later on. We go from 1, let's say, to 4 in this case, and then we have to say that AAA area, this is equal to the Y. How can I do this? This would be points. So the idea, let me, I guess I can stop this one here, but we will want to find the change in x, which is going to be this distance, this height of this trapezoid, times this y plus this y divided by 2. So we know that trapezoid area is equal to height times b1 plus b2, base 1 plus base 2 divided by 2. That's all we want to do. But notice that the height, it will always be written as xi plus 1 minus xi, okay? And this means that if we are moving clockwise, xi minus xi, this will be positive, okay? Again, we move here, it's going to be positive. We move this way, it is going to be positive because the next subsequent xi is larger than the previous one. But then if you come from this point 4 to point 3 is smaller than this one, the value of x I'm talking about, then we have a negative sign in the height. If this will be a negative sign in the height, then from the total area that we are trying to calculate, we will remove this triangle, okay? So imagine, if we are adding trapezoids carefully, going from this point to this point, we are adding the trapezoid plus the area of this trapezoid plus the area of this last trapezoid here, okay? So let me try to make this a little shorter. We go here, then we come down here. So you have a look for a moment and you can determine, let me try to identify some other color, but only maybe blue. I hope this is clear. No, it makes this is blue. Let's make this blue. This is blue, and this is blue. So traveling from this point around, we find the area of this trapezoid plus the area of this trapezoid plus the area of this trapezoid. For a moment, when you go back here, we will be subtracting the area here, which is this triangle. And then next point, we will be subtracting this other point area of this triangle here, which means that this total area which is defined on the top, removing these two, we really find the area of this polygon, which is going between points 1, 2, 3, 4, and 5. Okay, and we want now, we want to check is area between all the polygons, all the combinations. So now what we have drawn here, we have the area of the polygon which goes from 1 to 2 to 3 to 4 to 5. Good. What if we don't go, we go from 1 to 2, then not to 3, but imagine for a moment that we go to 5, and from 5 we go, yeah, it's going to be a little mixture because I have the diagonals, but if you like, we can take out the diagonals to make this one a little nicer. So if we remove the diagonals, we keep those values, but let's say we go 1, 2, let's draw another path. This is going to be 1 to 2, tell something, 4, 3, and I guess 5 is left. So we have 1, 2, 4, 1, 2, wait a second. We go from 1 to 2, from 2 to 4, which means that, no, okay. This is here, 2 to 4, and then from 4 to 3. So 4 to 3, then we have to remove this, and this comes here. Okay. Now the direction of the arrows is not correct. I think this is correct. 1, 2 to 4, 4 to 3, 4 to 3. Let me draw. Let's try to make this looking right. No, it should be like arrows like this. Okay. Why can't I show this one correctly? So yeah, it's maybe it's best if we put a little more weight. Okay, so we go 4 to 3, then we say 3 to 5. This is correct, and from 5 to 1, we just need to change the direction of this one. 5 to 1. This is going to be something like this. Okay, so now this is what we're trying to say. I hope that this much of directions it's useful for you, and we can give a break here and we can continue. We can discuss this topic in the next session. Thank you for your attention, and we'll see you in the next session.